Hello and welcome to YMT217 Programming Languages. Today we are going to discuss a new chapter, of course the first part of it, because this chapter is lengthy, and we will speak about evolution of major programming languages, how the programming languages that we are using today came to existence, the development process. Right before we start discussing all these details, of course covering all the process in one chapter is not possible. So what we have is like selective ideas about the pathway of the development until our today is technology, or the available technology today. All right, so what are we going to discuss in particular? With a programming language, one of the earliest actually versions of the programming languages, the way we see it today, or at least at a draft of the way we see it today. And the programming language itself was named Plan Calcul, and it was designed or developed by 217. This is the way they pronounce it, it's a German name, so if you want to properly pronounce it, it's said 217. This person developed the language, and it's actually the rough translation of this is a program calculus. It's like a program that finds or does calculus or arithmetic and similar jobs. We will speak about it in details. Why? Because it has a lot of roots of the development we have today, the modern development of programming languages. We will speak also about minimal hardware programming and why we needed to have such programming languages, for what reason. Those we refer to by something called pseudocodes. Pseudocodes in our reality, we explained about them before to you, is like a fake code, a code like written text describing the process of solving a question or solving a problem. Yet, when we speak about those here in the context of minimal hardware programming, we speak about programming languages, but in the context of back then programming. All right. So let's go ahead and discuss 217's programming language or program calculus. It was designed actually around the mid of 40s. So you can see it's really old. The design itself is old, and of course in the realm of programming. Early times of digital computing. It's extremely early time. But the idea of the development itself was not discovered back then until 72. What is meant by the name Plan Calcul means programming calculus by their own language. This is the rough translation. And what was it for actually? I will explain in a few seconds, but before that I would like to tell that this programming language was not implemented. And being not implemented, that is also a problem that didn't make it popular. Although it was back then a great development in terms of programming languages, but it was known much later than its own invention time. And that was one of the reasons it didn't become popular back then. All right. Before we go ahead, why do we need a programming language? Now let's think about a hardware, a machine that we have in terms of its hardware. How can we communicate with it? In order for us to communicate with a machine, we need to know the language that the machine understands. The language that a machine understands is only one language, which is series of ones and zeros, or the machine code, or the binary language. And we explain about this in logic circuits for those who are taking logic circuits with me. If you are not taking it, no problem. Just understand that the machine itself has its own language to run its process, and this language is composed of series of ones and zeros as codes to do things. Alright, so if we want to speak to the computer, we need to speak to it by the language that it understands. How do we understand ones and zeros? Then we have to learn what these ones and zeros may or can represent. Therefore, in order for us to design or develop a program, we need to write it in a machine language if we have no other way to communicate with our machine. That was the early time of programming. All right, so they write a program literally by like English-like codes, or you can say pseudocodes, or maybe even algorithms. It's like a way of solving or a method of solving, steps for solving the problem. Then they convert these steps to a machine code directly. So you can imagine the effort that they needed to do back then. Why? If you want just to do a process, an arithmetic operation, how will you do it? You need to understand how the computer does it by its own codes. That was not easy. I'm not going to explain it now. We will have a chapter for it. It's simple. I mean, representation of machine language, how it does it by certain codes, series of ones and zeros, and how it takes from memory, it carries from memory things based on these codes. So in order for us, we human beings, understand high-level language, a language that's closer to our understanding, let's say English, the one we speak with now, and the machine language, series of ones and zeros, we have a main problem, which is the translation. Well, we can write the process or the way or the algorithm for solving the question or the the program that we need to create, then code it in a machine language. Well, that's possible. Theoretically, practically is extremely hard and difficult. So here comes the idea of how about we create a translator that does this job for us. Okay, this is exactly the idea here. How about we create something similar to the high-level language, and then that does the interpretation by certain way, in an intermediate way. All right, so this is the concept, and we'll speak actually about assembly later on, because it's like an intermediate between the high-level language we have today and the machine language. But for the time being, before assembly, this is even before assembly, the whole idea now. What do we have with this programming language? What we had as a data type, now imagine when in current or modern day programming languages, we have different types of data, but back then there was only one type, which is a single bit. And from this single bit, we could create other types. So what kind of features we had or were available with this data or this programming language? Basically, we had structures. Structures actually are records. If you have any idea about C or C++, you will understand what I'm saying. If you don't, imagine it is like a record of things that you can compose different data types under one name. Okay, a bit similar to class. Of course, it's not a bit similar, right? We could also use floating point, and that's extremely important. Back then, there was a problem with dealing with floating point. Now, if I say floating point, you may think like, why do we need to have a problem with floating point? Yes, with the machines that we have now, there is no problem. Back then, there was a huge problem. Although with complex mathematical operations, now floating point also poses always a problem with like detailed calculations, yet you may not be aware of. However, it was back then a major problem, and now in basic sense it is not. We had arrays, records, and so on. So that was the basic understanding of the language itself, the abilities that we had. Now, let's say, could we write a program with this language where we can make a loop? It was possible. There was like a for, similar to the for that we know in our programming languages these days. You possibly could make a loop. There was also some sort of scripting or specifying some levels or some tags so that you can go somewhere and back then. That means maybe you can put labels for iterative statements, but there was no go-to. You could just maybe loop with nesting loops based on scripting or subscripts here. That's possible, but a bit hard. It's a bit primitive compared to what we have now. There was structured statements like selection statements, but there was no else. So you could use similar to if statement, but not else, and that's also a problem. All right, what else did we have in this programming language as a feature? we could represent mathematical expressions that were included, and it was possible for variables, like similar to the languages that we know today and we have today. All right, what could this language do back then? Well, we could do a lot of things with arithmetic operations, arrays, also more complex things like connectivity of a graph, things operated on integer, floating point numbers, maybe like a bit more advanced square root and so on. These were, maybe you think like, square root is complicated. Yeah, back then was not easy. Creating a function for a square root back then was a major issue. Why? You are dealing with a machine, you're just trying to reach the machine's level by some certain way or method. All right, one more thing. There were like things like more complicated as playing chess. There was also an algorithm for it using this language. Also, the developer didn't forget the concept of precedence. He set up 6 different levels for precedence. You guys are aware of precedence and what it means. The precedence here, we speak about which comes first. If we have multiplication, addition, which comes first? So the one with the higher priority or more or higher level of precedence. All right. Okay. The thing is, the developer didn't just have only one version. He created actually more developed versions, or at least one more developed version of the early time. The main problem with this kind of language, or this specific language that we are speaking about, was like this. Now, he could create a language that is close to our understanding, high level, close to that. It's not exactly like now, but it was difficult to script it, the notation of the language. What do I mean by notation? If you want to write, now let's say, if you want to write a program that multiplies 2 variables in Java, in C++, in C, in C#, in any programming language that you use, you'll just be using maybe 2 or 3 lines. Let's see, now for this one, if we want to apply something similar, how many lines do we write, or do we need to write? Let's just think about this. Let's say for one statement, how many lines do I need to write? Now let's just check, just one statement. The first line was most like statements of current languages. It may be definition, maybe declaration or so on. The second one most likely is optional, but still we need to provide something about the subscript if we are using an array. So we need to provide the subscripts, from which array to which array, from which subscript to which subscript, and so on. The last line is about the data type. Now let me show you in reality. If we want to assign, let's say, this expression a of 4 or a4 as a subscript plus 1 to a5. Now look, initially this is the description, first line. It's similar to the language that we have, but different assignment statement. Then the second line we need to put the subscript. The third line we need to provide the data type. This is integer, so we speak about integers. This refers to integer in this particular language. And in that case, is it not complicated? Somehow it is. And back then it was a bit complicated for scripting. So it's not that much far away from machine code. We are still, again, with notation problem. We get stuck with notation problem. However, this kind of attempt was really great, although it was not discovered at an early time, but yet it was back then a major milestone in the programming language realm. All right. Now, as I said at the beginning of my explanation, machines were extremely limited in terms of their capacity, the memory, in terms of their CPUs. The running process was slow. It wasn't easy for people back then to run programming languages or to do an extensive development and run it on the machine. One more thing. The problem with machines also back then, they didn't have the supporting tools or software. There was no concept of window or any operating system the one we know today. They were limited with extremely elementary operating systems that just run the machine itself. Imagine I give you a simple example like DOS. Of course, not exactly same, but I give that simple example. So if you need to know DOS, you need to deal with a lot of instructions in order for you to run a process, not just few mouse clicks or keyboard strokes. That is the major problem. Add to that a limited main memory, there was no concept even of a hard disk. Later on it came, but the idea is you are limited in many things, in processing speed, in processing capacity, in main memory capacity. All these things were limiting the ability of people to produce extensive programming languages. So they had to go with the available possibilities. All right. So we have a problem with the machine language. Why with machines? Why do not we write directly with the machine language? And as I said earlier, writing with the machine language was possible. So it's possible for us to translate everything we write in our language to a machine language. But is that effective? Of course not. Why? Readability problem. We explain about the concept of readability. Modifiability also. If you do not understand, how will you modify? That's also a problem. Coding itself was really hard. You need to learn all the codes in binary, ones and zeros, 1101. For example, all these things you need to learn them. The operational codes, the operands, the memory addresses, all these things you need to learn how you code them in machine language. So you will put inside you a manual, and every time you will just flip a page to learn about these codes, and that was not easy. Plus, there was something extremely difficult with indexing, or what we call floating point issues that I explained earlier, that we don't have today. Machine was limited, extremely limited. When dealing with big numbers, it wasn't enough for you to accommodate for the length of the floating point number. So these limited the machine code itself from being popular in programming. All right, okay, machine code is not easy, is not flexible, it has a readability problem, it has modifiability problem, it is hard to learn, it's hard to code with, it's hard to understand. What should we do? Back again, the idea is creating a programming language that we understand, or at least we can have a sense of, and then we apply this programming language to the machine with an intermediate, some interpreter or a compiler. We explained about this in the last chapter. All right. So what happened? What came next is what we call pseudocodes. Pseudocodes means actually, and literally means by itself, the pseudocode, the word pseudocode, mean a fake code or something like a code. In current days, we use it for a general description of the code that I'm going to write. It's not exactly written by one specific language. It can be fit, or it can fit any language that you are interested in once you write it. It's a fake code or a code like text. Then you can transfer it to a code. But what we refer to by here, pseudocodes, is something like an early design of programming language. What is this early design of a programming language? We have different types, and even if you read from different books or watch different videos from other people, they may present different types of pseudocodes, or actually early primitive programming languages that were used back in time. All right. One of the major development was designed, or was actually published or written by Markley in 1949. There was a language called shortcode. This is its name, shortcode, designed by Markley in 1949, and it was written specifically for binary automatic computers. This is the idea. If you remember from Introduction to Computer Science, this kind of generation of computers, the BNAC, it's famous as a milestone of computer development, the new computer development that we have in our life, or in our today's technology. So back then, Markley designed or created a a short code or a programming language can run with this computer, then the idea was transferred to the next generation of BNAC. What was the next generation? It was Universal Automatic Computer version 1, or UNIVAC. So it was adopted, the same programming language, but maybe with some modification, and it was set on UNIVAC 1. Right. The idea of the programming language itself was not really published. It wasn't published. There is no exact, you can say, reference that tells you all its details where you can find it with its own ISBN or whatever. No, rather there are different versions of it in manuals, so you can get it through manuals. I think there is at least one manual kept, the original one, and some copies of it. So what do we have in this programming language, and what kind of features do we have? Well, initially it allows you to do mathematical expressions. Now, the first thing comes to our mind: why do we always say mathematical expressions? Why do we speak about arithmetic? It was a major problem back then. In early 40s, early 50s, the biggest problem, the biggest challenge was to them is the scientific calculations, dealing with floating point number, big calculations. Back then it wasn't easy, and they were developing a lot of scientific things rely on mathematical expressions. Complicated things like square root, the exponential, logarithms, and so on. And for that reason, they were running different programming languages to get mathematical expressions done in an automatic way, or an automated way, using the computer. All right, so how do we represent whatever data we have or values we have in computer? There was something we call byte pair values, right? So the codes themselves were represented by something we call byte pair values, and we could represent those, whatever we have from these expressions written in the language using this, and I will give you some example soon. Now look at this. Now think about an expression. Whatever expression you want to write, it would be coded something like this, like from left to right. Now think about, this is the representation. It could be exactly coded this way, and everything had by its own code for an expression. Okay, do you need to know this language? No, you don't have to. You just need to know that there was some language like this represents equations and operations by certain codes in order for them to accommodate for a programming language. So what's good about this language and what's bad about it? Okay, initially it was good in the sense of it's closer to our understanding. If you write something like this, it's close to us, we understand it. So even if it is coded like this, look, 00x0 03 20 06 y0. Okay, it's an expression. How do I understand what it is? Now look at this. X0 refers to a variable in this case. How about 03 refers to some function? How about 20? I read a 20 earlier. It's just 20 or, well, it's just a code for the absolute, then so on. We have also for parentheses and so on, until you reach the last variable or the last component. All right, sorry, I said earlier 03 is for equal, 20 is for square root, and 06 for the absolute, and then y0 is the variable that we have here. Now how about 00? It was just padding, filling up space. What do we mean by a space? Now the representation of the language itself, you see codes. Do I know it? I'm also not very familiar with this language, so you don't have to know it. You just need to know or understand how it is represented. Now if you have an expression like this, it is likely that we will have these blocks. Now count 1 2 3 4 5 6. These blocks were represented by, in binary, 12 bits each. So we have these blocks or byte pairs of 6. If you multiply 12 by 6, that's 72 bits each of those. Okay, And in that case, if you do not have this one filled, then you have to fill it up by zeros. That was padding back then. How about multiplication? Multiplication was exactly referred to by the way we refer to it in algebra. You just place the two variables next to each other without placing anything. So if you want to multiply x0 and y0, you just place them x0, y0 directly. You don't do anything else. There was no expression. It's like what we have in our algebra today as AB means A times B. All right. The language itself was not implemented. It was actually purely interpreted. And the process itself was called automatic programming. And this is what I want you to understand. The idea of moving from manual interpretation or manual translation to automatic translation or automatic interpretation, or if you like in modern days, compilation with maybe hybrid even compilation and interpretation process. All right. Well, is it easier than previous attempts of programming or doing programming with programming language, with the machine language, sorry? Yes, it is. But at what cost? So what are we losing by having such an interpretation process? It was delaying the process. The translation itself, short code interpretation, or not translation, actually interpretation, I would define it. This is an interpretation process. Was approximately taking 50 times slower than the machine code. So you just need to write a multiplication process. If it is run by 1 second, let's say, just an assumption, in your own machine language, it would take 50 seconds based on short code. Of course, the process is much faster than that. Let's say one multiplication process is done by, let's say, 1 nanosecond. It will take 50 nanoseconds approximately by such an interpretation, and that is really slow. That slows down the process. Any other pseudocodes? Yes, for sure. There was something we call speed coding. It was developed by Beckes in 1954 for IBM 701, one of the earliest versions of IBM computers. And the idea of this speed coding, the idea of this one is overcoming the limitations of short code. How about if we can run an interpretation in a faster way and accommodate for more things? Okay, that's good. How can we do it? How about we extend the machine language to include floating point operations? How will you do that? Well, we create a language that accommodates for this extension. The same concept that we apply today. Well, okay, then how can we do it? We can use instructions, so the instructions and operations for arithmetic and math functions. Okay, then good. What else? Conditional, unconditional statements, branching, also possible with the language. Auto increment of registers. Why do we speak about registers? Because we carry whatever available in the memory to registers before processing or right after processing. This is how it is even done in modern day, except for some advanced computers, and we will speak about them in their time, not now. All right. There was also a certain mechanism for array access based on also incremental registers or whatever. The main limitation with this kind of language is exactly that we have a limited space. The programming language itself here was interpreted, okay, and we had this interpreter, you can call, installed by itself. So its implementation was limiting whatever available in the IBM as a memory. When you need to use an interpreter, this interpreter has to be realized somewhere in your machine. Because it's not manually done, then we have to make the computer understand it. So it has to be somehow implemented in the computer so that the computer understands how to deal with it. All right, so what was left back then from this IBM 700 as a memory? It was just 700 words left for your program. 700 words, that's extremely little. You can check what it means, 700 words in our today's technology. It's literally nothing. It's literally nothing. It's simply that you are left with a tiny space for your program. That limits your ability of programming. How about other pseudocodes? There were attempts from different teams. We can't refer to all of them, but the most common ones, for example, there was for the universal automatic computer, there was a compiling system. Now, pay attention to this. This one was developed by a team led by Grace Hopper, and they developed some languages with different some language with different versions. They called this language arithmetic language version 0, 1, and 2. So it was, the initial one was arithmetic language version 0. They refer to it by A-0 or A0 in short, if you like. The next version was A1. The one next to it, the last, was A2. So what was the idea? What was the main idea? Well, okay, the primitive programming language style, what we call now pseudocodes back then, how about we expand it into machine code again with the same concept of speed coding, but we accommodate for also the expansion of computing systems. So that was the main idea. A very similar thing was also done by Wheeler, and it was from a different part also in the world, the idea of having some method to locate addresses. Now this thing I would like to speak about. Now we said about expanding, using memory efficiently, expanding also the programming language into machine language. Well, what's the big deal about it? Well, if we expand a programming language, we need to have a mechanism to accommodate its expansion. All right, so what is the major factor in dealing with computer memory? Is reaching out to the addresses of this memory. Do I have an automatic way or automated way for reaching the addresses of the memory? What do I mean by the addresses of a memory? Now, let's simplify it a bit in our modern day understanding. Imagine the memory as a series of vacant parking lots next to each other, just next to each other. They are vacant, they are empty, and each one is written or labeled by an address. Let me take the pen. So we have like a parking lot with different parking lots, and these are labeled, let's say 1, 2, 3, or whatever you like. Okay, and then you need to access to those based on what? Based on their exact addressing. Now, there is no exact address by one in memory, especially nowadays. There is a different type of addressing. Usually we refer to it in hexadecimal. However, if you want to access to it, you need to catch its address. You need to know its address. It's like locating a house. You locate it by its address. That was exactly the concept of the memory. Imagine it as like this parking lot, vacant with different, not necessarily vacant, maybe there is a content inside of it, but with certain labels or addresses in this case. We need a way or a method to locate these addresses. So if we can get an automated way to locate these addresses and deal with them, then we solve most of the programming languages problem. Now, today's computing or today's programming languages do not have a problem with locating addresses. Back then, there was something we call absolute addressing, and it was a problem. Absolute addressing was slowing down the process, the whole process, and wasn't efficient. So Wheeler developed some way or created a method for locatable addresses that we can locate by an automatic way. This is the end of this session. I'll create another session very soon. Until then, have a good time. Goodbye.